When we talk about artificial intelligence, we often imagine a computer thinking exactly like a human. And while it might seem like a digital miracle, the engine driving modern AI borrows its core design directly from the biological human brain. In our last video, we looked at how machine learning allows computers to figure things out from data instead of following a list of instructions. The specific structure that makes that kind of learning possible is what we call a neural network. The blueprint for this comes from inside your head, where billions of tiny cells called neurons constantly fire signals to one another across branching pathways. Years ago, computer scientists built a digital version of this process. They created an artificial node. You can think of this node as a simple digital relay station. It receives a signal, processes it, and passes it on. A neural network is just thousands of these nodes organized into columns. Information flows through these columns like a chain of command, starting with the raw data on the left, passing through several stages of processing in the middle, and ending with a final result on the right. Because this grid is built to be flexible, it doesn't need a human to write rigid rules for every situation. Instead, it processes information much like human instinct. To see how this actually works, think of the network as a digital assembly line. Let's say we want it to look at a picture and decide if it's a starfish or a sea urchin. We start by feeding the raw pixels of that image into the first column of nodes. Every node in that first column is connected to the next by digital pathways. These connections have weights, which you can think of as the level of importance the network gives to a specific detail. A thick connection means the node is paying close attention, while a thin connection means it's mostly ignoring that piece of data. As the image data moves down the assembly line, each column examines the incoming signals, applies those weighted priorities, and hands off its conclusion to the next column. The information finally reaches the end of the line, where the network makes its final guess. In this case, it confidently labels our starfish as a sea urchin. Making a guess is only half the battle. The machine must realize it made a mistake and change its behavior for the next time. Our network takes its sea urchin guess and compares it to the correct answer. It immediately realizes it failed. This starts a correction process. A warning signal pushes backward from the end of the line, traveling all the way through the grid to alert every node exactly where the logic failed. The network fine-tunes those connections automatically. It thins out the pathways that led to the wrong answer and strengthens the ones that point toward the right one. In the early days of computing, researchers had to manually plug and unplug masses of physical wires to change these connections. Today, a digital network runs this trial and error cycle of guessing, failing, and rewiring itself millions of times in the blink of an eye. This is how artificial intelligence learns. It isn't magic. It's a relentless mathematical loop of making a prediction, finding the error, and adjusting those internal pathways until the mistake disappears. Recognizing a simple shape is one thing, but harder tasks require a much bigger grid. This is where we get the industry term deep learning. The word deep simply refers to the scale of the architecture. Instead of just a few columns of nodes, we add dozens or even hundreds of them between the start and the finish. This allows the machine to learn in stages. The very first column doesn't look at the whole picture. It only searches for basic shapes, like straight lines or curves. It passes those lines to the next column, which combines them into more complex patterns, like rough star shapes or circular textures. The deepest parts of the grid take those patterns and assemble them into a full, recognizable object. Because of this incredible depth, AI can move past seeing raw pixels and start to understand complex human contexts. This layered learning happens every time you unlock your smartphone. A deep network is scanning an invisible grid of points to recognize your unique features. It's the same engine helping voice assistants understand your speech and allowing medical software to spot tiny health issues in a hospital scan. This capability doesn't come from a programmer writing out every possible rule for the computer to follow. Instead, the system relies on that massive grid of connections, guessing, finding its own errors, and learning to get it right, one mistake at a time.